In this video, I'll be discussing the main concepts in the circular motion unit. To begin with, I have here a series of relationships and equations that you should be familiar with as you're going into the assessments on this unit. On the left, we have a set of proportionalities. I say that the centripetal force is directly proportional to the mass. Also, the centripetal force is inversely proportional to the radius, and the centripetal force is proportional to the square of the speed. And so I'm going to go through a couple examples of how that plays out. If we were to double a mass in a given situation, keeping radius and the speed the same, if we were to double the mass, we would double the force. If we quadruple the mass, we'd quadruple the force. So they're just one-to-one like that. There's a relationship where one is proportional to the other in that way. The radius, however, is inversely proportional to the centripetal force. So if we increase the radius, we are actually decreasing the centripetal force, and it works also as multiples here. So if you're doubling the radius, you're cutting the centripetal force in half. If you triple the radius, you're cutting the centripetal force into 1/3. If you quadruple the radius, you are cutting the centripetal force in 1/4. All right, I could keep going. 10 times the radius, 1/10 the centripetal force. That's how that goes. For the speed, the centripetal force is proportional to the square of the speed. So whatever you do in terms of multiplying the speed, you have to square that to figure out what impact it has on the force. So for instance, if we doubled the speed, we have 2 times the speed, you square that, we get 4 times the centripetal force. If you tripled the speed, you square that, you have 9 times the centripetal force. If you quadruple the speed, then you have 16 times the centripetal force. 10 times the speed, that would be 100 times the centripetal force. So just keeping that relationship in mind and how those are related to one another will help you with some of the problems on this worksheet. The other thing you need to know is these equations over here. You should have these memorized. Centripetal force is mass times the speed squared over the radius. Speed is distance over time, or sometimes we rearrange that same equation and we do time is distance over speed. That will just help you out through this process. Additionally, you need to know some basic stuff about circular geometry. The circumference is 2 times pi times r, for instance. But you'll see as that comes up as we go through this. So the first problem here is taking advantage of those proportionality relationships that we talked about. So A, for number 1 here, says an object is traveling in a circular path and it experiences a force of 75 newtons when the radius of the circle is 2 meters. If the radius is increased to 10 meters, but the speed and mass remain unchanged, what is the new force? So in each of these problems you ask, what is changing? All right? The radius is changing. How did it change? We multiply the radius times 5. All right? And then you need to remember that centripetal force is proportional to 1 over the radius. All right, so as the radius increases, the centripetal force decreases. The radius was multiplied by 5, so the centripetal force is going to be divided by 5. If we take 75 and we divide it by 5, we get 15 newtons. All right. For part B here, again, look at it, see what's changing. It says that we have triple the mass, all right? And so if we have triple the mass, and you know that centripetal force and mass are directly proportional to one another, if we triple the mass, we triple the force, all right? So all you have to do is triple the force that you were given originally, so 0.2 times 3, all right, and you end up with 0.6 newtons. Oops. Okay. On the last one here, there are a couple things changing. First of all, it says that the speed went from 1 meter per second to 2 meters per second. So we've doubled the speed. Secondly, it says that the radius went from 50 centimeters to 2 meters. There's a little bit of a unit conversion in there, but 50 centimeters is half of a meter. All right, so if we went from 50 centimeters to 2 meters, we quadrupled the radius. All right, so you have to think here then, we're bringing in FC proportional to speed squared as well as FC is proportional to 1 over the radius. All right? But in this case, what we have is we start with our 20 newtons. Because we doubled the speed, we square that, and we have 4 times, here I'll just do 20 times. We have 4 times the force because we've doubled the speed. So 20 times 4. All right, now we have 4 times the radius, but radius and centripetal force are inversely proportional, so we divide it by 4 or multiply it by 1/4. And if you do that, you end up getting 20 newtons back out of the end. And so what happens here is the increase in speed is offset by the increase in the radius. All right, problem number 2. What we've got here is we've got an issue where we have to find speed to plug it into the centripetal force equation. It gives you some information about a racetrack. It says that a race car is going around this semicircular path and that it takes it 20 seconds to get around the semicircle. All right, and then we've been given some information here. We know the radius is 200 meters. And so the first thing that you have to do is you have to think, all right, if the circumference of this circle is 2 pi r, that's 2 pi times the radius, which is 200. All right, then we get 400 pi for the circumference. Now, we didn't go around the entire thing, we just went around half of the circle. So what we know here then is that the distance traveled equals 200 pi. All right, speed is equal to distance traveled over time, all right, which equals 200 pi divided by the time it took, which was 20 seconds. And when you do that, you get 31.4 meters per second. So in a lot of these problems, you're going to be set up like this. I don't give you speed directly. You have to look at how far it's traveled. You have to look at how long it took, and then you calculate speed from that. After we know that, then we're going to do something like this. We're going to say, all right, Fc equals ms squared over r. All right, we have all of these things. So Fc equals the mass, which is 1,500, times the speed, which we just calculated, 31.4 squared, over the radius, which is 200. And if you calculate that, you get an Fc equal to 7,402 newtons, approximately. It could be, somewhere near that, somewhere near 7,400. All right, and then the last thing it asks here is it asks what sort of force is this? Well, a concept from this is anytime a car is driving down the road or turning around a corner or anything like that, the force that is moving the car the way it is a friction force that exists between the tires of the car and the road. So we have to keep in mind that this is a friction force. All right. I often explain that if you were trying to make a turn and you were on a frozen lake with ice, or just imagine when you're driving around in the winter, if it's icy out and you try and turn, you can't turn. You just keep going straight forward in whatever direction you're going. And the reason is because in order to turn, you need good friction between the tires and the road. When there's no friction, you can't turn. All right, for this next one, we have, it says a 30-kilogram child on a merry-go-round in the park. It says the radius of the merry-go-round is 1.5 meters and it spins at a rate of 1 revolution per second. And then ask what the centripetal force is. All right, so on this one, it's extremely similar. We have to figure out the speed first. I know that it makes 1 revolution per second. And so again, I'm going to find the circumference of this circle. The circumference is 2 pi r. R in this case is 1.5. All right, and if you calculate that, you get 3 pi for the circumference. All right, we know that it goes around that entire distance, that entire circumference, in 1 second. It says it's 1 revolution per second. So it goes around the entire 3 pi meters of the circumference in 1 second. So for our speed, all right, we know the distance it traveled is all the way around the, we do distance over time. We know the distance it traveled is all the way around the circle, which is 3 pi. And we also know that it took it 1 second to do it. All right, and then when we get that for our speed, we get 9.42 meters per second. Then the last thing we need to do is plug this into the FC equation. The centripetal force equals m times s squared over the radius. In this case, the child is 30 kilograms times the speed squared, that's 9.42 squared over the radius, which in this case is 1.5. And then if you calculate that, you should get somewhere in the neighborhood of 1,774 newtons. Something I mentioned with this problem is if you think about the weight of the child is 30 kilograms. That means their gravitational force is 300 newtons. All right, 300 newtons then is what this child is used to experiencing as they're walking around, pulling them towards the ground. 1,774, that's almost 6 times the gravitational force that the child would feel. And so we say that this child is pulling almost 6 G's of acceleration as they're going around. So this is really, really fast that this would be spinning. And it's likely that the child wouldn't be able to hold on very well and that they would go flying off if the merry-go-round was going this quickly. And so that's why it's good to keep things slow when you're going around a merry-go-round. Lots of kids get hurt when they get thrown off merry-go-rounds that are going too fast. All right, number 4, this one is talking about a restaurant that is on a rotating tower. And it says the restaurant has a radius of 20 meters, and then there's a salt shaker that's sitting on a table near the window, meaning it's near the outside of that 20 meters. And then it takes 10 minutes for it to go around once. And then I ask for the force on the salt shaker. So this is very similar, again, to the same process that we've done before. What we have to do is we have to figure out the distance that it's going. We have to figure out how long it took. Most of this stuff is just given to us, but we have to use that circumference equation once again. So we know that speed equals distance over time. All right, in this case, the distance is 1 full rotation, again, so 1 full circumference. So I'm just going to write it in here this time. That's 2 times pi times 20, because that is the radius there, 2 pi r for the circumference, and divided by the time. Now, you have to keep in mind that 10 minutes is the time, but we need the time in seconds, so we have to convert that to seconds. There are 60 seconds in a minute, so in 10 minutes there are 600 seconds. All right, so we put 600 down here for the time, and we multiply that out. Oops. And what we get here then is 0.209 meters per second for the speed. Now we need to plug that into the centripetal force equation. We get Fc equals ms squared over r. The salt shaker is 100 grams. We have to convert that to kilograms. So there are 1,000 grams in a kilogram. So we divide by 1,000, and we get 0.1 for the mass times the speed squared, 0.209 squared over the radius, in this case is 20. All right, and when we do that, we get 0.000218 newtons, or you could say that it is 2.18 times 10 to the negative 4th newtons. That's the same thing. Notice here that this is a very, very small force. So it's taking a long time to go around the entire circle once, 10 whole minutes, all right, which means the speed is very low. And if the speed is low and the mass is low, we're going to end up with a really, really low force here. And that's what's happened. Okay, the problems on the front of this sheet have something fundamentally different about them than the problems on the back. All of the problems on the front of the sheet were traveling in horizontal circles, meaning like they were, if you take a circle, it'd be like parallel to the ground, okay? In each of these problems that we're going to be doing next, it has a vertical circle, which means the circle is going up and down. All right. The significance is that we didn't really take gravity into effect with the other ones because gravity was acting perpendicularly to the circle. In this case, gravity is interacting because the circle is vertical. As we go through these problems, that might not make a whole lot of sense to you now, but I'll point it out when we get through how having a vertical circle impacts things because we have to take into account gravity. So in this one it says that there's a 100 kilogram person riding a roller coaster, and I want the apparent weight when they're directly at the bottom of the hill, that their speed is 12 meters per second. I've also said that the radius of the valley and the hill are both 15 meters. And so the first thing you have to do is, we're going to be talking about the valley first. You have to find your circle in here, all right? And this is kind of, roughly speaking, outlining the circle that we're dealing with. So down here in the valley, we're at the bottom of the circle, and that means the force and the acceleration are going to be going upward. All right, and then if you identify that the acceleration is upward, when you make the force diagram on this one, which is where we're going to start, there are two forces acting on it. There's a gravitational force pushing the car down, but there's also a normal force between the track and the car, and so that's pushing it up. All right, or you could consider this the normal force acting on the person from the bottom of the car. But actually something significant here is because the object is accelerating upward, that normal force should be bigger than the gravitational force. So I tried to draw that noticeably larger there. All right, the normal force is more than the gravitational force. Because it's accelerating upward, it's accelerating towards that center of the circle. The next thing we know is that the gravitational force is equal to 1,000 newtons. We know this because the mass is 100, and so you just multiply by 10. So the next thing I'll do is I'll figure out what the value of my centripetal force is. For the centripetal force, we take m times s squared over r, which in this case equals 100 times 12 squared over 15. And if you do that, you should find that Fc equals 960. Right, and then this asks for the apparent weight. Something important to remember about the centripetal force is that it's an unbalanced force. What it does is it tells us how unbalanced the forces are. So when we get an Fc of 960, it says that the up and down forces are unbalanced, and they're unbalanced by 960 newtons, meaning there's a 960 newton difference between the upward and the downward force. We know the upward force is larger in this case because it's accelerating upward, and we know the difference is 960, and we have 1,000 already for gravity, so hopefully it makes sense that we'd call this 1,960 newtons, because 1,960 newtons is what it would take to create an unbalanced force of 960 going upward. All right, and so that is our final answer on this one. The apparent weight is the normal force acting on a person that's pushing them up. It's opposing gravity here. And so this person feels like they weigh 1,960 newtons, as opposed to normally they feel like they weigh 1,000 newtons, and so they're feeling extra heavy at the bottom of this hill. Problem 6 is very similar. We've got an object, it's on the hill, all right, but in this one, the difference is if you find your circle, the circle is actually traced out this way. And so if you are on the hill, you are actually at the top of the circle, which means that the acceleration is going to be going downward. The centripetal force is going to be going downward. And so we're going to have a larger force going down than what is going up on this problem. And if that's the case, then we draw in here our force diagram. We've got Fg going down, and then we've got a smaller Fn going upward. And the reason for that is because, again, it's accelerating downward at the top of the hill. We know, again, that this Fg is 1,000 newtons because the gravitational force is related to the mass, and the mass is still 100. To figure out what this normal force is, we have to do something similar to what we had done before, where we say, all right, Fc equals m times s squared over r, which is equal to 100. And then I gave you in this case that the speed is 8 squared over the radius, which is still 15. All right, because I said the radius was 15 for both the hill and the valley. If you go through and multiply those, you get 427 newtons. All right, and so this tells us these two forces are unbalanced by 427, or the difference between these two forces is 427. But in this case, we know that normal force is smaller than the gravitational force because the direction of acceleration is downward. So instead of adding here, we end up subtracting. We take 1,000 minus 427, and we get 573 newtons. All right, and so in this one, the apparent weight is equal to 573 newtons. At the top of a hill when you're on a roller coaster, or in a car for that matter, you feel light. All right, your apparent weight is less than your actual weight. On number 7, we've got a boy. This is kind of a similar type of problem. The boy is swinging. He's essentially here at the bottom of a circle, and so his acceleration approximately is going to be upward. All right, so we know that the larger force needs to be pointing upward. If you think about the forces acting on this boy, we've got gravitational force, which is going downward. We also have a tensional force, which is going upward. And actually, I'm going to make that gravitational force even smaller so that you can really see that it's smaller than the tension force. All right, because this object, as I said, we know is accelerating upward. Because if you look at this circle, right, the circle is something like this. Pointing towards the center of the circle is in this way, all right? And so we know that it's going to be an upward force as you do that. All right, so it's a 20 kilogram boy, so 200 newtons is the gravitational force. We're going to do exactly the same process to figure out how unbalanced the forces are. We've got Fc equals ms squared over the radius, all right, which equals, in this case, 20 times his speed is only 1 meter per second, all right, and it's over the radius, which is 10 meters. So if you go ahead and do that, you should get 2 newtons for the unbalanced force. And so if these two forces are unbalanced by 2 newtons and the upward force is larger, then this is 202 newtons. So Ft equals 202 newtons. So as you're going through and doing this, hopefully you can see how these all relate together. One thing to mention, I'm going to go back to what I was saying before. Hopefully now you can see what I was saying about these being vertical. All right, the direction of the circle is vertical, meaning that the centripetal force is either pointing up or the centripetal force is pointing down. And if that's the case, then we have to consider gravity as part of that centripetal force, all right, as part of the balance. Whereas if you're going around in a circle, all right, where the plane of the circle is parallel to the plane of the ground, then there's no gravitational component to that. If that's confusing to you still, feel free to come in and ask me. I'm not going to do the challenge question. It's pretty complicated. If you want to see the answer to that, you can come in and talk with me, or if you just want to check and see if you got it right, I will let you know. But I won't be doing that in this video. And as always, if you have any questions on any of the problems on this sheet, make sure that you come in and ask before the assessment. I think it's important that we work those questions out ahead of time so that you're not super confused going into the exam.